Dear learners, welcome to today's session. The topic of today's session is in fact linear search, and we will discuss also the bubble sort. In today's topic, basically we will cover two things. One is linear search, a kind of searching method, its example, as well as we will also discuss the time complexity of it along with the space complexity. And another topic we will discuss is that of bubble sort. Also we will discuss the method, example, as well as the complexity analysis, both time and space complexity analysis. So let me start from the first, that is linear search. So we all know that our computer systems is used for storing large amount of data, and many times we require to search data from the list of the records. So there are various methods which are available for it, like we have linear search, that is one method. Apart from linear search, we have other methods like binary search, we have interpolation search, we have median search. So linear search is very simple, and we iterate in this method all the elements of the list starting from the first location till last. So either we get the desired element or we do not find the element if it is not available in the list. So I will like to explain it with the help of an example. Here in this slide you can see we have been given a list of elements which is stored in the form of array, and the indexing of the array is from 0 to n minus 1. So there are 12 elements, so 0 to 11 is the indexing, and at respective index the elements or keys are stored in random order, and our target is to search a particular key whether it is present or not. If it is present, then at which location it is present. In this, let me try to search the element 10 whether it is present or not. So as I told that in linear search, we compare the element to be searched starting from the first location, and we proceed one by one till last location until we do not get the desired element. So in this example we can see that we will compare the key 10 from the first key stored in the array, and the first key is 50. So we can say it is not matching, it is not found. Then we will move toward the next location, and again we will compare it with the key to be searched. Now again we can see in this the key at current location is 4, which is not matching with the desired element to be searched. So we move to the next position, and so on. So till we reach it to the desired location where the key is matching with the element to be searched. So now we can display a successful message that this particular key to be searched is present at this particular location into the list of element. That is how the linear search work. So the advantage of this linear search is that here the elements are in random order, means the list of elements from which the searching is required to be performed, it is arranged randomly. So we are starting from the first location and moving till the last location till we find the element or we did not find the element if it is not present. Now comes the complexity analysis. So I would like to discuss the time complexity here. So as we know that in time complexity we discuss three types of complexity. What is the best case time complexity of the algorithm, what is the worst case, and what is the average case. So is the case with linear search. In the linear search, if we talk about the best case, so the best case situation will be when the key to be searched is found at first location itself. So we can say in that case the time complexity will be order of 1. And the worst case, if we complete the searching from the entire list and came to know that the element to be searched is present at the last location. So in that case, it will give us the worst case situation, worst case time complexity. It is represented by order of n, where n is the number of elements. For example, if we have 100 list present into the array and the element to be searched is present at the 100th location as last element, because we are starting to search from the first location, we will repeat the process till 100 times to reach the last location. So that's why its time complexity will be order of 100, where 100 is the list of elements. So in generalized way, we can say it is order of n. And in average case, it may be present anywhere between first to last location, or we can say on average case it is we are required to search half of the list. So it may be order of n by 2. N by 2 number of searching operations are required. So in big O notation, that this n by 2 is approximately of order of n. So average case time complexity of linear search is represented by order of n. So that is about the linear search. Now I would like to come to the second topic of today's discussion, that is bubble sort. So we know that sorting is required for many applications, where we require to arrange the element in some intended order, like in increasing order or in decreasing order. So it have various applications, like in bubble sort, the elements are required, binary search, the condition is that the elements should be in sorted order, or in binary search tree we require to sort the elements. So there are various methods which are used for sorting purpose. So bubble sort is one of the method. The other methods are like insertion sort, selection sort, quick sort, heap sort, cell sort, and so many others, merge sort. So today we are going to discuss bubble sort and we will see what is its time complexity. And one more thing I would like to tell here, that the selection of the method for sorting depends on the nature of the problem. Whether one should use the bubble sort, whether one should use the selection sort, insertion sort, quick sort, merge sort, or what kind of sorting method should be used, it depends on the nature of the problem as well as its time complexity. So less the time complexity of a method, better is the method to be used. So let me discuss the bubble sort. In bubble sort, basically this sorting method works on repeatedly swapping of adjacent elements until the list of elements are arranged in some intended order, whether in increasing order if we want or in decreasing order. Why it is called bubble sort? Because the movement of array elements resembles the movement of air bubbles in water, that is why it is called bubble sort. And array elements in bubble sort basically moves to the end of each iteration just as bubbles in water rise to the surface. Meaning to say that in this sort we compare first two elements initially, and then we see whether the first element is smaller than the second element or greater than. If we want to arrange the list in increasing order and the first element is bigger than the second element, then swapping will be required. So once swapping is being done, then in next step, next iteration, we will compare the second element with the third one. And if second is greater than the third, then again the swapping will be required. And in this way, next time we will do the comparison with the third element with the fourth, and accordingly if swapping required we will do, otherwise not, and fourth with the fifth. So at last the biggest element will be transferred to the last location of the list, and this completes one pass of sorting, we can say. So in the first pass, the largest element will be available or positioned at the last position, and then we do the same process again and try to fix the second largest element to the second last position of the array. And in next pass, we try to fix the third largest element to the third last position of the array. So this process continue till the second smallest element is positioned at the second position. So let me discuss it with the help of one example. Here we have 8 elements which are arranged in an array randomly. So bubble sort says that in pass 1 we try to place the largest element at the last location, or we can say each element is required to be placed at its correct position in every pass. So in the first pass, largest element at the last location, in the second pass, the second largest element at the second last position, and so on. So here in this example, pass 1, what we will do, we will compare the first element with the second element. So here we can see that the first element is 50 and second is 4. So 50 is greater than 4, so it will be swapped. That is, 4 will be transferred to the first location and 50 will be transferred to the second location. That is, first location means index 0, second location index 1. As we know that in array the indexing starts from 0 till n minus 1. So index 0 means first location of the array. So once we perform the swapping, fourth will be at first location, first position, 50 will be at second position. Then in next iteration, that is I is equal to 1, 50 and 55 are compared. So here in this we can say 50 is smaller than 55. So no swapping is required. And then we move to the next iteration, that is third. Now 55 and 25 are compared as shown in the bottom of this slide. So because 55 is greater than 25, so swapping is required. So 55 will be positioned at the fourth location, index number 3, and 25 will be positioned to the third location, index number 2, and so on. Similarly, in the next step, if we move forward, the 55 again will be compared with 10, and because 55 is greater than 10, swapping will be done. Next time 55 again with next element, adjacent element, that is 40. Again the swapping will be required because 55 is greater than 40. And next step 55 will be compared with 36 and so on. So in the last step we can see that 55 is placed at its appropriate place. So 55 is the largest element and it is placed at the last position. Now except the 55, remaining are still in unsorted order. So what we will do? We will again repeat the same process in next pass, that is we will compare again the first element with the second, second with the third, third with the fourth, and accordingly swiping will be done if required, and we will do this up to n minus 1 position, that is index number n minus 2. And after doing this, the second largest element will be placed at the second last position. Here it is shown in this slide, pass 2. So 4 is compared with 50, 4 is smaller, no swiping. Next, two elements are compared, 50 and 25. So 50 is greater and 25 is smaller, so both will be swapped. Their location will be changed, interchanged. So 25 will be placed at second position, second location, and 50 will be placed to the third. So in next iteration, 50 will be compared with 10, and because 50 is greater, again swapping will be done, and so on. So if we complete this pass, at the end we can see in the last figure, that is right bottom, that 50 is placed at its appropriate place. Now next pass starts. Again the same process will be repeated, but now it will be done till third last location, because last two elements are already placed at its appropriate place. So in pass 3 or step 3, again first will be compared with the second, no swiping because 4 is smaller. Then 25 with 10, swiping will be done because 25 is greater than 10. And next step, 25 will be compared with 40. Swiping will not be done because 25 is smaller than 40. So in this way we continue till the end of this pass, that is up to iteration number 6, and this 40 is placed at its appropriate place. So that is end of the pass 3 or step number 3, and the same process is repeated for the next pass. So same process is done, and now the fourth largest element is placed at its appropriate place, as we can see in the last diagram. So this process is repeated, in fact, n minus 1 passes. If we have n number of elements, so this process is repeated n minus 1 passes. For example, if we have say 10 number of elements, so total 9 passes are required in worst case. In worst case 9 passes will be there, and in each pass, in the pass number 1, there will be n minus 1 comparisons, and in worst case n minus 1 swiping also. Like in pass 1, we can see that there are total 8 iterations, because there are 8 elements, so 8 iterations are there, and in worst case 8 swiping may be done. 8 or less than 8 swiping will be required, and 8 comparison operation will be required. Similarly, in step number 2, we can see that there are 7 iterations which are required to sort the second largest element. In the third pass or third step, we require 6 iterations. So starting from the n number of iterations from pass 1, we are decreasing by 1 in every pass. So in the pass 2, we required n minus 1 iterations, in pass number 3 n minus 2 iterations, and so on, and total number of passes will be n minus 1. The purpose of explaining this is that this can be used to analyze the time complexity of the algorithm. So let me discuss, before we discuss the time complexity and space complexity, let me discuss the algorithm, how this bubble sort algorithm works. So here in this one, this function, bubble sort function is written in C programming language. So the name of the function is bubble sort, and its return type is void, that is we are not returning any value. There are two arguments which are passed in this function. One is the int numbers array. This is the array in which the list of unsorted elements are stored. And the second parameter is n, that is how many elements, how many keys are there into the array. So these two parameters are passed in this function, and thereafter we declare three variables I, j and temp. Basically, in bubble sort there are two loops which are required, one for pass as I explained in the earlier example, and another for the iteration. So for the pass we have declared variable I, and for iterations within the pass I have declared variable j, and temp is another variable which is required to store the data temporarily while swapping process is being performed. So we can see that in the outer loop I is equal to 0 to I less than n and I plus plus. So how many time worst case it will execute? It will execute n times. I is equal to 0, 1, 2, 3 up to n minus 1. And for every I is equal to I, this inner loop j will execute in fact from I is equal to j is equal to 1 to less than equal to n minus I minus 1. So when I is 0, it will execute till n minus 1 less than equal to n minus 1. If say n is 10, so it will execute 9 times. And this if condition, it compares two adjacent elements starting from j minus 1. When j is 1, so j minus 1 means j, it is 0, index number 0. Index number 0 of the array is the first element. So first element and number j is 1. So first number, that is 0th index element, and one index element will be compared, that is first and second element will be compared. If the first element is greater, then only the body of the if will execute, that is swapping will be done. Otherwise the body of if will not be executed. Once it is done for j is equal to 1, so next time it will increase z by 1, that is j will become 2. So j will be 2. So again this will execute from 2 to n minus 1, and second, third element will be compared. Next iteration, third, fourth element will be compared, and at last, second last element will be compared. So that is how this algorithm will work and it will complete. Now I come to the point that what will be the time complexity of it. So in the best case situation will occur when the array is already sorted. So array is sorted, then in one pass we will come to know that all the elements are sorted. So in that case n minus 1 comparison will be required. So that is time complexity will be order of n. Worst case situation will be when the array is already sorted but in reverse order. In that case n minus 1 passes, and in every pass starting from n minus 1 to n minus 2 till 1 iterations will be required. So we can say the time complexity will be n plus n minus 1 plus n minus 2, that is it will be n minus 1 by 2, or we can say order of n square. So this is the worst case time complexity, and average case time complexity will also be order of n square. And if we discuss about the space complexity, because in this algorithm only a temporary variable is required to swap the element, so space will be increases by 1 for temp variable. So that is why its space complexity are order of 1. So now I would like to conclude it. So before that we see what is the advantage of this bubble sort. Basically it is very easy to implement and understand the sorting process, and it is stable. If we have multiple keys of same value, then it will be placed adjacent to each other. So in today's session we have discussed about the linear search, its introduction, example, time complexity, and also we discussed the bubble sort, introduction, its example, as well as time and space complexity. So in next session we will try to discuss some other sorting algorithms. So thank you for today's session.